Okay, let's see if you are back. I am back. 1 minute late. Okay, so where were we? We were talking about ways of defining the damping matrix for solving structural dynamics problems using the finite element method. We made some historical notion of Lord Rayleigh and his idea about combining the mass and stiffness properties of the system to define um, a damping coefficient. And then we wanted to generalize this to a multi-degree of freedom system. And I claim that we can do this in the straightforward way of simply just replacing the model parameters scalar values with their corresponding matrix values like this. And then in order to determine these constants, we can think of the critical value of the damping coefficient that we know from the vicious oscillator that it has this relation. And then the definition of the damping ratio, that is the damping coefficient over the critical damping coefficient. So the damping ratio has this relationship. So if we introduce the Rayleigh model into this expression, we can write the damping ratio on this form here as a function of the two parameters alpha and beta of the Rayleigh damping and the frequency of vibration, omega. So the Rayleigh damping will always look like this. It's a combination of a linear function and a hyperbola like this. We can here then also start talking about, let's say, a mass proportional part of the damping and a stiffness proportional part of the damping. So the mass proportional part is the one related to the parameter alpha. So it's the one that gives us this hyperbolic behavior here. And the stiffness proportional term is the one governed by beta, and it's this linear function. And then the total damping obtained from the Rayleigh damping model is given by the weighted sum of those two functions. So depending on how we choose alpha and beta, we will get different damping ratios as a function of the frequency here. So this is the drawback, of course, that this particular form of the Rayleigh damping will always give us a damping function that depends on the frequency in this way. So if we are only interested in one particular frequency, then we can always choose alpha and beta to fit that one frequency. But in general, we have several modes of vibration. That's why we started doing this finite element model from the start, because it's difficult to find analytical models that represent general structures. So we will almost always need to consider the variation in frequency when we choose these Rayleigh damping parameters. So this was what I just said. And it's important to think about this. So you need to choose these parameters carefully in the general case. The way of doing this would be perhaps to prescribe. So if, for example, we have omega between 0.5 and 1 here, radians per second. This is the range of frequencies that we are mainly interested in, and we made sure that other modes of vibration will not influence our response here. So we only need to focus on what damping values we would get for frequencies between 0.5 and 1 here. Then we might choose damping ratios at the two border values, 0.5 and 1. Like at these two frequencies, we want specific values for the damping ratio. And then by doing so, we would obtain two different equations here. And that way we can solve for alpha and beta. So, but this is straightforward. I think that will not be the big problem for you here. The point here is that now that we can choose, oh, sorry. Now we have moved on to the next topic here. So we have defined how to choose the Rayleigh damping parameters. And this, I think, is perhaps the most important way of modeling damping when you are working in the time domain. Because most commercial finite element codes give you only that option. In a linearized analysis in the time domain, you essentially have only Rayleigh damping to work with. But the most common way of solving structural dynamics problems in practice in our everyday engineering judgments is to use modal analysis. And as you know, this gives us a set of uncoupled linear and viciously damped oscillators. And they have this form here, where the Q's are the generalized coordinates of the corresponding modes, mode number I. The nice thing with the proportionally, with the lightly damped system is that we don't even need to care about the material damping or how damping is distributed in this case. Instead, if we know what modal damping ratios we should use or could use, we can simply specify them individually for each modal vibration. And if we start considering trying to do actual engineering judgments based on these theories, we will find in the standards related to dynamic analysis, in Eurocode, in old Swedish standards, and in other international standards, recommended values for the modal damping ratios for different materials. So typically pure steel structures have very low damping ratios, less than 1%. And then concrete structures, you will find values between, say, 0.7% and up to 2.5% maybe. We are often given a damping ratio directly from the problem if we start looking into the standards that we are often forced to use. And this is a good thing, really. So we don't have to take too much. It's wrong to say responsibility, but in choosing the damping ratio, as I mentioned before, the important thing is that we don't overestimate the damping that we have in the system when we do engineering judgments. So looking for the codes and their recommended lower bounds is a very good place to start. Modal damping can also be used if you have a little bit more freedom, if you are not totally forced to use this commercial code, if you are doing a little bit of programming of your own. The concept of modal damping can be transferred to problems in the time domain where we might want to use direct integration, perhaps because we want to introduce some small nonlinear aspect or something like that. So we need to do, we need a damping matrix that corresponds to the modal damping that we have ascribed from the standard. Like for an example, if we are doing a dynamic analysis of a railway bridge, according to the Eurocodes, if it's a steel bridge, perhaps we are forced by the design code to use a damping ratio of 0.5% on all modes of vibration. This is a quite hypothetical situation, and this equation that you see here and everything, this has grown out of my studies as a PhD student, really. And there we had this problem that how can we create a damping matrix to use in direct integration that corresponds to the assumption that all modes are equally damped. Because if you remember from if we use Rayleigh damping, it can be quite difficult if you have a wide band of frequencies and you want to have precisely the same damping ratio on all of them, it simply can't be done with this standard Rayleigh model. It should also be mentioned in this context that you can extend this to have more terms and different relations between M and K, and there exist some papers about this in the literature. But nevertheless, it's really difficult to get one that gives you precisely the same damping ratio on all modes of vibration. So this idea here is to use the modal matrix and assign in the modal domain the specific values at each mode of vibration that you want, and then transform this back to the physical domain and use that as a normal vicious damping matrix. But this matrix will be full. This should be noticed here, since this transformation here is operating on a diagonal matrix here. This vicious damping matrix will be full, and that's much more than what you would get from the finite element discretization. So the finite element discretization gives us, in general, sparse matrices. So even if we have a million degree of freedoms, the matrix that we use to define the stiffness or the mass, it will still have 1 million elements on its main diagonal, but the off-diagonal values will be maybe a factor up to 100. So the total number of non-zeros in one of those sparse matrices would be like 1 million times 100. But in this case, you would get 1 million by 1 million if you drag this all the way. So this is not applicable for general systems. But it's an interesting aspect, I think, of how you can start working yourself around these quantities and these equations once you begin to understand them. But one thing that is really important and that you should know about is the concept of complex modulus. Because this is really a way of defining a frequency independent material damping, which is a quite common assumption and also common observation in mechanical systems that are relevant for us structural engineers. And as the name suggests, we simply define a complex modulus in the way that we take the constitutive matrix for our element and we multiply it with a complex factor that has its imaginary part related to the damping ratio that we would like to induce. So eta is the loss factor. It's equal to 2 times the damping ratio. So both of these quantities occur in different finite element codes, but the concept is the same. And by doing this, so I think maybe to cast a little bit of light on this, I should mention that for those of you who are familiar with the Fourier transform, you will know that if we apply that transform to this equation, its properties are such that this first derivative here, this will generate an imaginary number when we apply the Fourier transform here. And then when we apply the Fourier transform again, this imaginary number will become real because we multiply by I really here when we do the Fourier transform. So the Fourier transformation of the equation of motion that we are looking at here will give us a complex part, and that is the one related to the viscous term. So in the frequency domain, the viscous term gives us something imaginary. And this is what is reflected here, that okay, if in this mathematical model that we have used so successfully to model different civil engineering structures, we find that the Fourier transform gives us something a little bit strange. It gives us an imaginary term for how we model the damping. And we simply just accept that because it's just a mathematical model and it works quite well. So we use it, although it seems a bit strange to have something imaginary for something that we all know is actually real. But this is just an artifact of using this second order ordinary differential equation. So we accept the fact that the damping in this type of model is related to some imaginary number. And then we try to relate that imaginary number directly to the damping ratio that we would like and the material properties that we have. And then we end up with this complex modulus. And it's just as simple as this. We multiply the original constitutive matrix with a complex number, the imaginary part of which is equal to I times the loss factor, or I times 2 times the damping ratio that we would like. And this will give us a frequency independent damping. It will be the same for all frequencies. And then we sort of lose the viscous term here, and we relate we simply obtain the viscous part directly in the element stiffness in this way. So it's totally straightforward. We actually simply just multiply the stiffness matrix with that complex number that we defined previously. Also, if all elements have the same loss factor, then we can actually multiply the entire stiffness matrix of the global system with this one factor. So this can be used in different ways. But the point here is that if we have the same loss factor for the whole system, then this damping matrix, the corresponding damping matrix, will also be proportional. So this I mentioned already, that the imaginary unit comes somehow from jumping between the time and the frequency domain. What happens when we do this is that if we stay in the frequency domain with the complex modulus, then everything is fine. We don't worry so much. But if we have a damping ratio defined in this way, and we solve the problem in the frequency domain, and then we apply the inverse Fourier transform to see the result in the time domain, then we will find that this idea is non-physical in the sense that it creates a non-causal behavior. This means that actually when we go back to the time domain with this solution, we will find that at time equals 0, where nothing could have happened with the system, still we will have a small displacement there already. This is, I would say, an artifact of the way that we construct damping in this way. So this only works well for weakly damped problems. The more damping we introduce in this way, the larger the non-causal effect will be. So this is something that one should keep in mind when one uses this complex modulus. So now we have talked quite much about this equation of motion and different aspects of how to add the inertial terms to this equation in a realistic enough way to do engineering judgments based on linear structural dynamics. So the next step would be to actually implement this in an actual problem. So this will be a little bit of repetition and a little bit of let's say hygiene factors that we need to bring with us when we work with finite elements. Because in the end, now when we are talking about this at school and we are taking it very nice and slow, and there is no real stress here, then we can play around and do things in a creative way. But in practice, in reality, we need to be very, very structured when we work with finite element modeling. And this is, of course, because general commercial finite element softwares are very general. So we can model very complex structures. But we need to know, we need a strategy to deal with all the options and all the decisions that we have to make when we build a model. And the fundamental thing here to do is to start simple. Actually start with something like a simply supported Euler-Bernoulli beam, or something that we can even find a closed form solution for. And then we increase the geometrical complexity in steps. This is how to get it under control, because there are many mistakes that we can do when we use these commercial codes. And the manual is long. Some of the codes have very nice manuals, but some of them have very, let's say, sparse information. So we need to know a lot ourselves, and the things that we don't know or cannot know, we need to figure them out. And typically we do this by making tests or numerical experiments. And the first type of numerical experiment that we need to do is to ascertain that the mesh density is fine enough to represent the vibrations that we are interested in. But at the same time, in these early stages of modeling, we are not only interested in the errors that arise due to poor meshing, but we also need to ascertain that we model boundary conditions in a correct way, that all our constraints are created in a correct way. We need to check and double check that all our material parameters and loads and parameters related to loads are correct. So once we have decided that the mesh is appropriate for our problem, we simply start by increasing the complexity of the analysis procedure from there. So let's say we start out, we are going to do a simply supported steel concrete composite bridge. So the first model we make is just an Euler-Bernoulli beam with some equivalent section, and we make sure that we get everything right there. Okay, so we would start with some static load case, maybe gravity load or something else that is related to the problem at hand. And with this static load case, we can make sure that we can compare with some simple tabulated values for different basic load cases, and just check and make sure that the orders of magnitude of everything is reasonable and correct. And when we're happy with that, we compute the natural frequencies and the mode shapes. We solve the eigenvalue problem. Now, this can give us some guidance. Actually, if in the static load case we apply a gravity load, let's say, this force only works in one direction, and that could sort of hide errors in our model. So when we apply, when we solve the eigenvalue problem, we will get another aspect. Like now things will vibrate in all different possible directions. So simple mistakes in perhaps boundary conditions or some constraints can become apparent in an eigenvalue. I mean, when we study the eigenvectors, the modes of vibration. And since they are moving in a more general way than the static load cases that we might have started with, they can, apart from giving us a new quantity to test against a known model that we know is correct, it may also reveal, let's say, pieces of your model that are not fitted together in the right way. That is, if some of the internal constraints are not well defined, you might see things that vibrate in ways that they shouldn't be able to. So this gives us a second line of defense, let's say, to find all those little errors that we typically make every day. Then, when we are happy with all of these things, only then do we start to apply the actual dynamic load cases. If we are doing this in a time domain analysis, using an implicit or explicit method to integrate the equations of motion, if it's a fairly large system, this third stage is what will be, this will be the most time consuming part. So before we start that, we want to be as sure as possible that everything is okay with our model. So we don't spend a lot of time waiting for a solution that in the end turns out to be erroneous, and we could have figured that out before. So this is like this is the way we increase the complexity in the modeling by starting with a beam model, and then if we find it, if we find that we need something more complex, we add complexity in steps. And every time we create a new model, we have this like 1, 2, 3. Does it work correctly with static loads? Does the natural frequencies and mode shapes seem all right? If so, yes, let's do the dynamic analysis and run the train or cars or wind load or whatever it was that we were looking for in the beginning. And we always try to start with something that we can check against known solutions. Of course, when you get more experience and so on, you will do things in another way. But I think for the beginner and for the first few years of practicing as consultants or engineers, having a very strict way of modeling and checking your models, doing your checks on yourself is it's absolutely necessary, I would say. In choosing mesh densities and checking our models, it's nice to have some rules of thumb. And I think it's actually not so complicated, because we need to know something about the frequencies that we want to include in our analysis. And from those frequencies and the structural system, we can figure out what wavelengths will be relevant in the analysis. And once we know what wavelengths to model, I think this simple example is well enough. I mean, if we can divide the shortest wavelength that we want to include in our analysis into 8 pieces like this, 8 little segments, then I think it's quite obvious that we will be able to pick up that wave motion or vibration that corresponds to this minimum wavelength that we include in the analysis. So I have this far not seen any case where following this rule of thumb gives a bad approximation. On the contrary, when you start to have really large problems, you might want to reduce this a little bit. And I still think that we find quite good solutions, even if we divide this by 6 instead of 8. But the mesh density has some other interesting things that happen. Because one thing that happens when we start to do dynamic analysis is that apart from the structure moving and changing its state of deformation over time, now also the loads can move over time. So sometimes we find that we need to increase the mesh density to be able to model moving loads in an accurate way. So we do get a few more things to think about here, really, when we do dynamics. But moving loads and so on is quite uncommon, I would say, in the everyday engineering work that we do. But if we get to some more advanced studies, perhaps with high-speed railways, we will need to think about these things. And then comes, and again, I should say that this I'm only giving here like some practical guidelines for how to do this. I don't go at all into the theories of how to solve systems of equations with numerical methods. I expect you to have an idea as to how these things can be done from the basic courses in numerical analysis. I do find that in using finite element method in practice, so at least I have to go back to the basic books and check things and make sure that I remember things right and everything. That you need to do a little bit of repetition continuously to really feel that you know what you're doing. So a nice book on the numerical methods that we use should be in the bookshelf for the first few years at least, if you're working this type of problems in practice. But there are, like, once you get over that threshold, you can again set up some rules of thumb that make life really easy. And I think here, in choosing the time step, we need to consider the time variation in the applied loads, of course, just as we need to discretize space here to be able to represent the wavelengths that we are looking for. We also need to discretize time in a way that can describe the variation in the loads. Another thing is related to the frequencies that we are interested in. So in the example, when we were talking about the mass matrices before, we found that for the first few modes, we had really small errors as compared between the different methods that we used. But for the last modes, we find some really strange errors and some really large errors. So before we start doing a dynamic analysis, we have to consider what frequency range we are interested in. And so if we use the modal analysis, then the frequency range is sort of defined by how we choose modes of vibration, right? Because the modes of vibration are connected to the natural frequencies. So if we take the 10 first modes and say that the first mode is maybe at 2 Hertz and the last one is at 30 Hertz. If we use the modal approach to the analysis, then this inherently limits the frequency range to the modes that we choose. But if we are doing a time integration, the frequency range will be defined by how we define the time step and the total time of the analysis. So actually, if we do a time domain analysis, it might occur that we think in our heads that we are considering the first 5 modes, but in reality, since this is in the sense of time a continuous function, if we use time domain methods to solve the equations of motion, we will include all the frequencies that our discretized time can represent. So we might need to actually filter the results in the end, if it is that we are actually limiting ourselves to a certain frequency range. So we need to know that the highest frequency that we want to include is correctly described, but we also need to think that we might have a wider frequency band than we expected. And then, of course, if we're doing time integration, the time step must also be chosen so that we can ensure that the integration procedure is stable. And I guess it goes without saying that we also need to assure that it's accurate. Now I said it anyway, but of course this is important. So it's very important to think about the highest frequency of interest when we set up an analysis like this. It can have different implications on the analysis, depending on how we solve the equations of motion. And again, this is also connected very closely to the convergence study that we do on the mesh. So we have to make sure that the mesh, that the solution is converged in terms of eigenfrequencies up to that highest frequency. So I said that I wasn't going to talk too much about the actual methods of solving these problems, but there are some rules of thumb that can be easily picked up from the literature. And so if we use implicit integration with unconditionally stable methods, this recommendation is quite common, that you need a time step that is smaller than a tenth of the shortest period or involved in the analysis. So this means that the highest frequency is divided into 10 segments. That way we can be absolutely sure that we pick up all the peaks of interest. It should also be noted that there are implicit integration schemes which are only conditionally stable. So if you choose a too large time step in those implicit schemes, you will have exploding solutions anyway. These are rarely implemented though in commercial finite element programs. So I think it's safe to say that in the commercial codes, you will only be subjected to these unconditionally stable methods. And if you dare go outside this box and do stuff on your own, of course you are expected, you are obviously reading and learning how to do that. So then you will have to figure out those details for yourself. Okay, so then here there are some interesting things here actually about conditionally stable methods and explicit integration. And it's this thing here. For the central difference method, a stable time step is obtained if this relation holds here. So delta t has to be less than or equal to over the maximum circular frequency that we have in the problem. So this is for an undamped problem. What's interesting here and why I brought this up is that if you have a damped system, you have an even tougher criteria here, that you need to choose an even smaller time step. And this is for me quite counterintuitive, because I would expect the damping to sort of help the system become more stable. Actually, in some numerical methods, they use damping to stabilize the problem. But in this particular case, damping does not work in that way. And this is quite interesting. But this is all this kind of stuff that you will find in the basic literature about these topics. So if you need them, you will find these. Then we have a more general setting. A critical time step could also be defined in this way, where L is the element length and Cp here is the dilatational p-wave speed of the material in question. So this is also sometimes called the p-wave modulus or the oleometric modulus. This is not always conservative, but if you have some really complicated problem with many different materials and different structural elements that are modeled in different ways, you might need to consider something like this. And what this says is that if we choose the time step in this means that the P wave cannot skip any elements in one single time step. So the wave will always, if we choose the time step in this way, the wave will always at least go from one element to the other in one time step. So here is a picture just to illustrate if for some reason somebody doesn't pick up the idea of a dilatational wave. This figure in the top here is supposed to show you how the wave motion works here. So we have dilatation, that is either the material is being compressed or is being stretched. And this is how the wave propagates. And the particle motion is in the direction of the propagation of the wave. For the shear wave, which is the other type of wave that occurs in the inside of elastic solids, here the direction of the particle motion is transverse to the direction of the wave propagation. Now these types of waves they only occur when we look at solids really. So in beams and common structural systems that we look at for bridges, we typically don't consider these waves, because then these waves would propagate in the actual structural materials, that is in concrete or steel. But these materials are so stiff that these waves have frequencies that are way outside our scope of interest. But the concepts are needed anyway, and they will come back to you in the case of earthquake engineering. So it is a good idea to look a little bit at these things if you want to apply structural dynamics in settings where wave propagation becomes relevant. But this is outside the topic of this course here. So in the same way that we can discretize time, we can also discretize frequency, and this lies implicitly here. So this you will have picked up already. I think you have done some exercises with a little bit of signal analysis, or maybe I'm wrong and that comes afterwards. Then you will learn more about this later on. But the frequency domain and the Fourier transform, I think, if you don't know about these things and you really want to do structural dynamics, I strongly urge you to learn about the Fourier transform, because this is so central to everything that we do here. We like to see things in the time domain. It's intuitive in one way, because we can understand how things vibrate. But when we can start seeing things from the perspective of the frequency domain, this is really where the analysis is going on when you're doing practical decision making around this. You have to be able to do this jump quite freely. And it also gives us a very nice way of solving the equation of motion and a way of analyzing the equation of motion. So as long as we stay in the linear domain, if we have a linearized problem, we can always apply this Fourier transform on the equation of motion, and we will end up with something like this here. So now, what was before a system of second order ordinary differential equations is now a linear system of equations that it depends on frequency only. So if we rewrite this, the system matrix here, and put it all together as a matrix function of frequency like this, then we see that the Fourier transformed equation of motion has the exactly same form as the statical problem that we are so used to dealing with. It's only that all these quantities are dependent on frequencies, so we need to solve them for a number of frequencies to be able to do an analysis. But the solution procedure now is that of solving a system of linear equations for each frequency of interest. So at each frequency, we need to compute this inverse somehow. But then for each frequency, we know how the system wants to behave. So this is a little bit like a continuous eigenvalue problem, really. Only that we don't just pick out the eigenvalues, we pick out everything that happens in between the eigenvalues as well. And we also pick up from this problem the damped eigenvalues and the influence of the damping on how different modes interact. So this equation here characterizes the behavior of our system. And actually, we use this very much without thinking about it. So if we would compute these inverses for all relevant frequencies and put them together in a three-dimensional matrix, then we would have here what is called the frequency response function of the system. So the frequency response function is the consequence of actually assigning the right-hand side to be a unit matrix. We apply unit forces at each degree of freedom, and we solve for those. And this is like a frequency domain influence line for our problem. So we know the behavior for a unit input, then clearly we should be able to use this for arbitrary inputs in some way. And I will illustrate this with an example here. This is a model of a two-dimensional model of a portal frame bridge. So it looks like this. Here's one shear wall here, another shear wall there, and a plate on the top like that. And at these three different locations, I have plotted the frequency response functions corresponding to loads acting in the corresponding degree of freedom. So this line here, it involves a horizontal load acting at the horizontal degree of freedom in this point here. And so it should be mentioned here that this portal frame bridge is coupled with the model of the foundations that includes the wave propagation and the dynamics that go on in the substructure. In the foundation. So there are no boundary conditions on this node. So we can put a force there and we can get a response. And in this case, it would look something like this. And here we see that the fundamental mode is activated. Even if we are putting a force here in the horizontal direction, we get a little bit of energy. Or here probably the fundamental mode. Yes, the fundamental mode is a horizontal mode here. So at 4.6 Hertz, we have a mode where the whole structure wants to vibrate in the horizontal direction like this. And this, if we do the eigenvalue problem, we will only get like this one discrete value here at 4.6. And then we will get the next discrete value here and the one here and so on. So solving the frequency response function gives us the same information, a little bit more accurate if we include the damping, as the eigenfrequency problem. But at the same time, it gives us the characterization of the system as a continuous function of frequency. So if we can just describe the modeling also in the frequency domain, then if we look at this equation here, you see, if we can describe the force in the frequency domain, all we need to do is to multiply the force with the frequency response function. And then we will have the solution in the frequency domain here. And then the obvious final step would be to apply the inverse Fourier transform to obtain the time domain solution for the corresponding problem. So this is the methodology that I use mostly for myself. So I do recommend that if you're not familiar with the Fourier transform and you think that structural dynamics is interesting and exciting, I would strongly urge you to become confident in using the Fourier transform and understanding these concepts. Okay, here are some references to the books that I would say number 1, 3, 4, and 5, and 6. Those are the ones that I would recommend for further reading here. I'm supposed to say a few words about exercise C1, and it's as simple as this. I think this is just to give you a little bit of structure as to how to approach this problem. There's nothing special about that. If you feel uncertain, look at this. Otherwise, don't hesitate to ask us. But I would like to spend a little bit of time to describe a few more practical examples. So this is a pedestrian bridge that, or I should have mentioned also, I work at a consultancy here in Stockholm, Sweden, called Thyrens. We have departments from all fields of civil engineering, and we work mainly in Sweden with Swedish projects, although we have some interesting collaborations in small scale in England and in Lithuania. Oh, here is a question. This is interesting. Let's see what happens. Rust, you want a Rust? Okay, let's take a short 5-minute break And then we will go, thank you also for pointing this out to me. I just keep talking. I love this. I just talk and talk. But you guys need a break. So we will take 5 minutes and then we will spend like 10, 15 minutes looking at a few examples, and I will present to you some suggestions for masterpieces topics. See you in 5 minutes. Thank you. Okay, so we had a short break. And now I will try to sum this up in a nice way by giving you some examples of how these theories can be used. So this is a pedestrian bridge that we at Tyréns designed quite a few years ago. It lies in Kallhäll here in Stockholm. And I sort of inherited this task from some structural designers within our buildings designers. They are working with buildings and bridges is quite different. So in this project, most of the project was creating the building around the station. So the task of designing these bridges also landed on their table, but those guys didn't have the experience to deal with this problem in a rational way. So they wanted to make a simplified model, and they did some combination of a beam model and a shell model, because they realized that this is very difficult to model using beam theory. I'm not sure if it's doable really. So they did use some shell elements to define the deck, but they wanted to model the superstructure, let's say the top part of the superstructure using beam elements. And instead of, these are all welded beams. Many of these are like standardized beams, but nevertheless, in order to mount these together in a good way, you need a lot of internal stiffeners and things here to make this work. And then in the design code, it says that, okay, if you have a vertical, if the natural frequency of the fundamental mode for vertical vibration is above 5 Hertz, then you don't need to consider dynamics at all for pedestrian bridges. And this is a sound assumption because people work with a frequency around 2 Hertz, and even if we try and run our fastest, 5 Hertz is simply too fast. We cannot do that. So any structure that has frequencies above 5 Hertz will be influenced by the overtones of the stepping frequency and not the fundamental frequency of the loading. So that's safe. So what they adopted the strategy of trying to design this bridge so as to get the frequency of the fundamental mode above 5 Hertz. And they did a lot of efforts to do that. And made some quite interesting mistakes in doing that. So when I got this problem, I was like, but there is no way for us to make this bridge have a frequency above 5 Hertz unless we do like ridiculous adjustments to the structural system and put a lot of material that is totally redundant and useless. So instead, let's say, if we read the Eurocode carefully, we see that the code acknowledges that it is very difficult to model this in an accurate way. So if the designer feels uncertain about how to do this, they can prescribe that the bridge owner should make a test. We design the bridge the best we can, and we make a test when it's built. And then we adapt the structure to introduce maybe a tune mass damper or some other means of mitigating these vibrations if they actually occur in reality. So with that strategy, I removed a lot of steel and I went back to a reasonable static design, and I find the first vertical bending mode at 3.4 Hertz, like this, and then the first torsional mode, which is also relevant in making these decisions, at 4.7 Hertz. So both of these are above the stepping frequencies that we're afraid of. And then here are some other modes of vibration that are totally irrelevant because the frequencies are so high. So apart from that, we don't care. And this is, I think, an important thing here, that it's very rarely a good idea to try to design so that the dynamics becomes irrelevant. In some cases it works, and if it's straightforward to do it, then we should do it. The problem with this is that we might end up in a situation where we're actually not designing a good product just because we're trying to meet one criteria. But we need a holistic perspective. If we are meeting the dynamics criteria with ridiculous static designs, then maybe we need to rethink the problem altogether. So the design code is not there to sort of relieve us from the decision making. The design code is there to give us structure to our decision making. But if we start to try to follow one particular condition or criteria, then we will get lost. But what we need to do here is to avoid frequencies that are involved in the walking phase and its overtones. This is like the design, the main point of design here. And in this case, we can't do it by structural modifications. So instead, we look for, how can we introduce more damping? And another factor that at that time seemed very important to me was about the support conditions. I now know that in this type of structures, the support conditions have very little effect. But in my PhD studies at the time, I was working very intensely with bearing friction. So this analysis is a bit colored by that. So first I did this convergence study on the mesh, and well, I've been doing this for some time, so I knew where to start, and this 50 millimeter mesh will be good. Then I ran one with a 25 millimeter just to make sure. And then we also made some assumptions about the bearing conditions. So this is a simply supported structure in the sense that one of the ends is fixed and the other one is free to move in the horizontal direction. And I was afraid that maybe the neutral axis of this beam would give a large eccentricity here, meaning that we would obtain large motions over the bearings when they actually move. And then the friction there would alter the dynamics of the system. So I also did some checks on that, but you see here, assuming a rolling bearing or a fixed bearing in the free end of the bridge doesn't really have that much implication on this problem. And then having done that, now we know it's just one mode that we need. We've been able to determine that we only need to study the fundamental mode for this bridge. So now we go to this single degree of freedom problem, and we use that as far as we can. So here we have the frequency response function for that one mode of vibration of relevance. And I get these modal parameters from the finite element code that I used. So the modal mass and the natural frequency. That way I can set up this frequency response given some damping ratio. And then the loading, if we remove the static part of the load, the walking load would look something like this. The light gray line here is the first component. And then we have the two overtones here in different dashes. And then we sum them together according to this. This comes from this book from Bachmann and Allman. This is a really nice book about vibrations in structures induced by man and machines. But I think it's the man part here that is a really nice starting point to learn about pedestrian bridges and how to model. So this is the load that they imply, and the Eurocode doesn't say anything about how we should model the load. It only gives us a few criteria. So these are decisions that we have to make ourselves. So on basis on that, I could set up a function here of the step frequency, that is how the acceleration varies with the step frequency. And then you see, since this is we are mainly interested in the resonance that can occur between the pedestrians and the structure, the damping ratio is the central parameter here, really. So the design code stipulates 0.5% damping, and that's also what we used, but it would be interesting to see what happens if we introduce a little bit more damping also. And then with the Eurocode recommendations, this structure should obtain accelerations limited by 0.7 meter per second square, given that 8 to 15 persons walk on the bridge. But this is a really simplistic way of saying that, because of an important aspect of pedestrians is that we as humans we are not so good at synchronizing ourselves. It's not so relevant either. We rarely need to synchronize our walking. But if we're just like 2 or 3 guys, it can happen that we get into a common pace. And of course, if 3 people are perfectly synchronized, this would give a larger dynamic amplification than having just one person being synchronized with the bridge. So this is a quite vague statement, actually, and it has caused a few discussions here in Sweden, because if you start considering like how pedestrians can synchronize, there is in the literature a model that looks like this. We have an amplification factor that we use to amplify the response for a given bridge, given that one person walks on it. And then we want to extend this to having several persons walking to it. And since we cannot synchronize so well, we need to reduce the total dynamic contribution from this group of pedestrians with respect to their unsynchronized behavior. So this factor does that. And as you can see here, if we have just one person, nothing much interesting happens. But if we have like 8 persons or 15 persons, in this case, we should follow this, the orange curve here. If we have 8 or 15 persons, it doesn't really matter so much. It alters the load with like 25% or something, if we consider their inability to synchronize. And it's very interesting to see if you extend this function to a wider range of pedestrians, that is also to larger bridges, if we assume that one person consumes about 1 square meter of space. Then 2,000 persons would mean that we have a bridge that is 10 meters wide and 200 meters long to fit all those people in there. So if we would fill that bridge, the dynamic contribution, according to this model, the dynamic factor will not scale with a factor of 2,000. It will scale with a factor around 25 or something. And this is a considerable reduction. So this is an important aspect to bear in mind when you look at the load that you need for pedestrian bridges. And so we were worried. I was worried. I did the dynamic design of this bridge and also the static design calculations. And I want to make sure that everything is okay. So I took the theory that I learned from Ride here in this course, the same as you, only a long time ago in my perspective, and set up this 2 degree of freedom system to study the dual mass damper that I would like to prepare this bridge for, in the eventuality that when we actually build the structure, people do feel unsafe to walk on it. We don't want that. So we want to be able to fix the problem. And it's as simple as this. We set up an analysis, call some guy who knows how to make a TMD, ask them what space requirements you need and what masses you can expect for the circumstances at hand. And then you set up this model to convince yourself that, you know, introducing a TMD at a good location can give us here, if we take a heavy TMD, 2.5 tons, the TMD motion will go from this red top here down to this blue curve down here. So this is a significant reduction. This is maybe 20 times or something. It's a very large reduction in the amplitude of vibration. On the other hand, we see that the TMD moves quite much. So we have to make sure that there is space enough for the TMD to move. And then with a lighter TMD, which of course would be easier to mount into the structure, because now 2.5 tons that is vibrating, we need to make sure that we have stiffeners and things that can bear this load. But a lighter TMD, of course, will give rise to smaller forces. At the same time, the capacity to reduce the vibrations is somewhat smaller, and the motion of the TMD becomes much larger. So maybe this TMD motion would be difficult to fit. If you remember what the structure looks like, the only place we can put the TMD here is underneath the bridge here. And there we have about 400 millimeters of vertical space. But it is not a problem to design both of these TMDs that I suggested here for that purpose. Another way of dealing with this is ongoing research now here. Maybe you have met Sara Tell. She is a PhD student here at KTH, working for Raed Karoumi, and she's working on this particular problem. Like, instead of mounting this TMD, that, you know, the point with the TMD is that we tune it to a certain frequency. So this needs to be maintained. This will detune itself over time, over 20, 30, 40, 50 years. So if you put a TMD, you also have to set up a maintenance scheme for that, and you have to make sure that it's actually followed. This type of solution, of course, any viscous damper will need maintenance too, but at least in this case, we don't care about this tuning aspect. We only care about the damping aspect. So it's easier, and it's also, like, this image here comes from early preliminary analysis around this. What we've learned now is that in most cases you can actually mount the damper directly over the bearings here. So you don't even need to take any space from the free space underneath the bridge. So with this type of devices, here's one example, and in this particular case we can get twice as much damping easily. And then of course we could get even more if we play around with the geometric parameters here, but this is a much more robust way of introducing extra damping in a pedestrian bridge like that. So that is a couple of, and the point here with this is really that if you look at Sara's papers, we introduced this damper in a quite general way in a single degree of freedom system based on the fundamental mode of vibration. And then, so the point is also that you can get really quite far with these single degree of freedom systems. And if it's possible to solve the problem with one of those, you should always go for it. But I also promised Raed that I would mention to you that we have some ongoing projects at Thulens where we are looking for students who have certain interests. And one thing, speaking of pedestrian bridges, is that I would like to set up a rather comprehensive measurement campaign where we go out to, with a simple instrumentation, measure the fundamental mode of a really large number of pedestrian bridges. And the purpose here is twofold. One is that we want to see how this CETRA is the French equivalent of the Swedish Transport Administration, well, the road administration. So they maintain all the French road bridges, and they also have a large responsibility for French pedestrian bridges, and they have made this guideline, which is really useful for designing engineers. So I would like to compare the results of the CETRA guide to a large number of Swedish pedestrian bridges to learn more about that. So there's a measurement campaign. And then, of course, once we have those natural frequencies of maybe the fundamental mode and 2 or 3 other modes, It would also be very interesting to do some mathematical modeling of all those bridges and see how we can adapt parameters in those to match the results and learn more about the uncertainties in this type of systems. There's also a lot going on with relation to data-driven analysis, and it would be interesting in this topic to see how many bridges do we need to start doing some data-driven analysis on that data, and what type of ideas would arise if we start fantasizing about having a really large data set for pedestrian bridges. And what could we learn from implementing data-driven analysis? That is machine learning, methods of machine learning. Very interesting. Continuously ongoing topic. This is my topic from my PhD studies, and I am still very interested in modeling of steel roller bearings. One of the researchers here, you have probably met Andreas Andersson. He's right now in the field measuring on a very interesting bridge that has steel roller bearings. The neighboring bridge to that one is one that I've been working on a bit myself, and that one has pot bearings instead. So now we will get some really interesting empirical data from that bridge. So if somebody is interested in bearings and friction modeling and a little bit of experimental data, then here we can find something interesting on a deep theoretical level, I would say. We are also working much with the photogrammetry for the time being, and we are very interested in modeling pedestrian bridges with photogrammetric modeling. So if somebody is familiar with these techniques and think that you would like to apply that on bridges, this is a great opportunity. This is about creating essentially building information models from photogrammetry. So we fly with a drone around the structure and take a lot of pictures, and then we build a model of the structure by triangulation in those pictures. So there are many interesting topics, but you need to be familiar with photogrammetry to get a nice start here. I think it will be difficult to start from scratch unless you are really willing to work hard. But modeling of bridges, thinking about automating flight patterns so that the inspector or drone pilot can, instead of focusing on what the drone is doing, this person can focus on other things on site. This is of course in relation to inspection of bridges. Also very interesting to see what open source software there are for photogrammetry. So this is something that I'm very interested in. But again, I do think that you need to have a little bit of knowledge about photogrammetry because a master thesis is just 20 weeks. So to really do something that is meaningful, to learn a completely new topic that is a bit off topic from what we are doing in civil engineering, I think it is not recommendable. But again, if there is somebody who is really interested in data-driven analysis and has a bit of knowledge about this already, then we are very interested in looking at how to deal with bridge maintenance data in a more general sense. And here again, we are thinking like 10 or 20 years into the future where all the inspection data is digitalized and stored in a data-friendly way that is manageable. So we would like to explore the potential of using data-driven analysis in large bridge management systems. And we are also very interested in simulating bridge maintenance data to be able to create proof of concepts of what can we expect. So how can we motivate bridge owners to invest in let's say unusually complicated data structures that you would need to actually be able to utilize data-driven analysis to its full potential. So civil engineering is a bit slow, but this is something that is growing very, very quickly now. And my suspicion is that at the point where society in general accepts this paradigm shift that lies in having autonomous vehicles moving around on our roads. When that day comes, data-driven analysis will penetrate all the corners of society, I think. Well, yes. Thank you for your attention. And if you are interested in discussing some of these topics for master theses, don't hesitate to contact me. I should write my email address here for you. There's something like that. You can reach me at, okay, but how do I, oh, only Epic Pro. Okay, so I will write it. Oh, this is going to be very difficult. This is not going to work out. Oh, wait, I have the pen. So the pen might work. Yes, my email address is like this. Maybe I get some intelligent comment here. Yeah, here, 2 comments. Yes, I will write it here. Sorry, how can I write it to everyone? Yeah, here we go. Yes. Thank you. I'm getting old, I'm feeling old. At tyrens.se. There, you can mail me. And we can have a more private discussion if there is some particular topic that you would be interested in. Of course, there is a limited number of participants and all of that, and it's not up to me to decide who goes where, but do report your interest if you would be interested in doing your master thesis with us at Tyrens. Otherwise, we can set it up also here at KTH if you don't care about being in an office with the current situation and blah, 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 everything, you still wouldn't have that really nice experience that you would have gotten in the pre-COVID historical period, because I myself, I sit at home working almost all the time. So actually, I don't know how we would organize this for this next spring, but you all are going to need a master thesis topic, and you're going to need some organization around that. So if any of these topics interest you, I'm willing to discuss that with you. Okay, so there's a question here from a person in the audience. Do you have any topic related to railway bridges infrastructure? Yes, I think that all the topics of 2, 3, and 4 can be geared towards railway bridges, if that is your particular interest. Modeling of bearings, I think, is an important topic in railway bridges, because we see that the friction, either rolling friction or sliding friction, can induce actually quite substantial additional damping contributions that the linear theory doesn't describe, and that the current standards doesn't give any real guidance as to how to use it. But that was the main issue when I presented my PhD thesis, that like how can we get bridge owners to accept more advanced analysis techniques and so on. If we can show that we get twice as much damping from an existing bridge, and if that leads to the situation where we can keep the bridge without doing any vibration mitigation things that would in turn lead to new maintenance needs and so on, that leads to a lot of savings in society. So this topic is really important for railway bridges, I would say. And then again, for structural dynamics, I don't currently have any other topics that are directly related to railway bridges. But instead, it's this maintenance data that is of my personal main concern right now. Like, how can we gather data? How should we keep data? And how can we analyze data in order to provide society with a more efficient and robust maintenance system, management system for these structures? This is my main concern right now. So this can be geared towards railway bridges, but those two topics will not have anything to do really with the structural dynamics. But if you have ideas of your own, you can also suggest those, of course. Are there any questions generally? You have been awfully quiet, all of you. Only these practical issues. Well, if not, I will again thank you for your attention. And I hope to see some of you at least in the master thesis process during the spring. You're very welcome. And thank you very much again. And good luck with the rest of the course.